All right, today we're going to crack open the casebook of a really powerful chemical detective. A technique so precise it can find one single clue hidden among millions of red herrings. Now, this isn't forensics, it's chemistry, and the technique is called polarography.
So let me ask you this. Imagine you've got this massive sample of water, and somewhere inside it there is a microscopic trace of something dangerous that you have to find. Maybe it's a heavy metal, maybe it's a critical vitamin. How on earth do you even begin to look for it?
Well, believe it or not, this is the exact kind of mystery that analytical chemists are solving every single day. They're kind of the guardians of quality, making sure our water is safe to drink, our food is nutritious, and our medicines are pure. So to solve these kinds of mysteries, a simple magnifying glass just isn't going to cut it, right? You need a really specialized tool, something that can do two critical things at once. First, identify the chemical suspect, and second, figure out exactly how much of it is there.
And that, my friends, brings us to the analyst's secret weapon. Let's pull back the curtain on a technique so revolutionary, it actually won a Nobel Prize and completely changed the game: polarography.
So, what is it really? Well, at its core, it's what we call an electrochemical method. You take your sample, you apply a slowly changing voltage, and then you just measure the electrical current that flows through it. And that measurement, believe it or not, gives you everything you need to know. It lets you identify what the substance is and quantify how much of it is present.
Okay, but the absolute genius of polargrapho, the thing that makes it so ridiculously powerful, is all hidden in its central component, a very, very special kind of electrode. And this is where things get, well, a little weird, honestly. The key to the whole operation is an electrode made of tiny, constantly falling drops of liquid mercury. Yep, you heard that right. It's called the dropping mercury electrode, or DME. So, why on earth would you use that? It sounds crazy, right? But this bizarre choice is actually a total stroke of genius. Think about it this way. A detective wouldn't want to use a contaminated tool. With the DME, every single drop of mercury provides a perfectly clean, brand new, smooth surface for the analysis. This constant renewal means every measurement is fresh and untainted, and that is the secret to getting incredibly reliable and repeatable results. Okay, so we've got our super special electrode ready to go. We run the analysis, and as we change the voltage, we get this unique graph called a polarogram. And you can think of this as the chemical's unique, undeniable fingerprint. This fingerprint shows up as a very distinct S-shaped curve. Now, it might look simple, but encoded inside the shape and the position of this S are the two critical pieces of information we need to crack our case wide open. Let's break it down. The first clue is all about where that curve shows up. The exact voltage right at the midpoint of that S-curve's rise, that's called the half-wave potential. Every chemical has its own unique half-wave potential. It's like a name tag. So if we see a curve at a specific voltage, boom, we know exactly what substance we're looking at. That's our suspect's identity. And the second clue, that's all about the height of the curve. The height of the top part of that S, the plateau, is called the diffusion current. This value is directly related to how much of the substance is in the sample. So a low curve means a low concentration, and a really high curve means a high concentration. This tells us exactly how much of our suspect is there. Now, of course, detective work is never perfect, is it? Sometimes you get what I'd call a smudged fingerprint. It's an abnormal, sharp peak on the graph called a polarographic maximum. This is basically just interference, and chemists have some pretty clever tricks to suppress it with other chemicals to make sure they get a clean, readable result. But what about the really, really tough cases? The ones where the clues are almost impossibly faint? Well, for those, chemists have developed even more advanced versions of this technique, upgrading the classic tool for modern challenges. A perfect example of this is something called pulse polarography. It's like a modern upgrade that can be up to 100 times more sensitive. Instead of a steady, slowly changing voltage, it applies it in short little pulses. This lets it easily separate the real signal from our substance from all the background electrical noise. It just makes that chemical fingerprint pop, even at incredibly low concentrations. Okay, so why does any of this matter to you or me? Well, this high-tech chemical detective work isn't just happening in some isolated lab somewhere. It's happening all around us, safeguarding our world in ways we probably never even see. I mean, the impact is absolutely huge.
In environmental chemistry, it's used to find those toxic heavy metals in our water supply. In the food industry, it's measuring the vitamins in your breakfast cereal. For pharmaceuticals, it's confirming the purity of medicines. It's even used for analyzing blood samples and identifying poisons in forensic cases.
So when you really think about it, it's pretty incredible. From a weird little electrode made of falling mercury drops, we get a technique that creates a precise chemical fingerprint. Polarography gives us the power to answer two of the most important questions in chemistry. What is in this sample, and exactly how much of it is there?
It's kind of like this silent guardian, working behind the scenes to keep us safe. And it really leaves you wondering, as our world gets more and more complex, what other invisible mysteries, the ones that are crucial to our health and safety, will this elegant technique help us to uncover next?